Okay, hello everyone. Today we are going to continue chapter 13, functions of several variables. We started chapter 13. We had class before the exam. I'm going to review that. Let's start. Okay, so if you remember, we talked about functions like f from, say, R2 or R3 to R. They were of the form f of x and y. So the difference with the functions we had seen before was that they had two or more than two variables. So one example we looked at was a function of this form, say square root of 64 minus x squared minus y squared. Okay, so just a quick review. The first thing we should do about any function is to find its domain. So we remember that when we have radical, what we have under the radical either should be positive or 0. So it should be greater or equal than 0. So either it should be positive or 0. We call this non-negative. Something which is either positive or it's 0, it's called non-negative. So 64 minus x squared minus y squared should be greater or equal than 0, which means x squared plus y squared should be less or equal than 64. Well, we can sketch the domain of this function. This actually describes the circle centered at the origin with radius 8. So this is the radius, it's 8. Now, the equation which describes this circle is x squared plus y squared equals 64. The area inside the circle is x squared plus y squared less or equal than 64. And the area outside the circle is x squared plus y squared. Sorry, strictly less than 64. And the area outside is strictly greater than 64. So here, because we have less or equal, the domain is the circle itself with the area inside the circle. Okay, that was the first thing to do. The second thing we need to understand here is that if we let z to show f of x and y, which is the square root of 64 minus x squared minus y squared, because on the right-hand side we have a radical, they are always non-negative. So they are greater or equal than 0. This means z is greater or equal than 0. Okay, that's the second thing to know. Now, we can actually sketch the graph of the function. Sketch. We can sketch the graph of the function. How? Well, z is equal to square root of 64 minus x squared minus y squared. If I square both sides of this equation, I can see z squared equals 64 minus x squared minus y squared. I can take minus x squared and minus y squared to the other side of the equation. What I'm going to see is x squared plus y squared plus z squared equals 64. This is the equation of an object inside three-dimensional space, x, y, z. This is actually equation of a sphere inside three-dimensional space with radius 8. Okay. But note that here we said z is always greater or equal than 0. So here above this xy plane, z is greater or equal than 0. Below this plane, z is negative. So we don't have z negative. Z should be greater or equal than 0. So this is not a part of the graph. This is the graph of the function. Okay, there are two questions. One is someone wants to see this slide. So here we computed the domain of the function. Which is the circle with radius 8 centered at the origin and everything which is inside that area. And here someone else has asked, is z always equal to f of x and y? Well, this is something I can do. I define the variable z. This notation, that's a good thing to say. If we have a sign of equality with two dots next to it like this, it means I define z to be f of x of y. That's a good thing to do. If I do that, then I can present the equation, then I can present the graph of the function in R3. Okay. So the next step was, the next thing we talked about, what they were so-called level curves. So when we have the graph of the function, we have here, so z is equal to f of x and y equals to square root of 64 minus x squared minus y squared. If we look at the graph of the function, we have semisphere with radius 8. So we can look at level curves. So here, if I look at the domain of the function is the sphere with radius 8 centered at the origin. So say this is 8, x and y. As I told you, you can think about level curves as curves on the map. So you can think about the graph of the function on the left side, say, as a real mountain. And the right-hand side, your domain, you can think about it as a map you have, okay? It's like you're looking at the mountain from above, and what you would see is like a map, which we have on the right-hand side. Now, level curves means we want to look at, so if it's a mountain, we can think about elevation from the sea level, for example. And we can look at the different heights. So, for example, we can look at the case where the elevation from the sea level is 0. In another sense, z, which is function f of x and y, is 0, right? It's exactly, if you look at the graph, these are exactly these points, the blue points. They are, the height of these points is 0. But we can write that also in terms of our equation. So it means square root of 64 minus x squared minus y squared is 0. If I square both sides, I would see x squared plus y squared is 64. It's exactly the equation of this circle here. Okay, so this is where the elevation from sea level is 0. This is the level set of 0. And then we can come a little higher. We can look at the points where the elevation from sea level is 1. Okay, so it would be something like this. These are the points which the height is 1. It means z equals f of x and y equals 1. Therefore, square root of 64 minus x squared minus y squared is 1. Again, here we can raise both sides of the equation. We can square both sides of the equation. What we would get is that x squared plus y squared equals 63. Well, what is that? X squared plus y squared equals 63. That's the equation of a circle centered at the origin with radius square root of 63, right? But what is the square root of 63? Well, it's almost equals to 8. It's actually 7.9. So it would be very close to the other circle. It's the circle with radius 7.9. Kind of like this. And we can continue that. We can look at the set of points where the elevation from sea level is 2 and etc. And we can sketch those level curves here, and they would become smaller and smaller until we get to the top of the mountain, to the peak, and that would correspond to this point here. This is actually what we saw on Tuesday. Now let's move to a more interesting example. So suppose we have another function which is it has two variables. Say f is from R2 to R, it means it has two independent variables. We show them with x and y, and it means it has one output. We show it with z. So we define z to be f of x and y. So let's say f of x and y is y squared minus x squared. Let's say that's our function. Okay. So we want to study this function. Again, what is the first step in order to study a function? The first step to see what is its domain. Well, there is no restriction on x and y. F is defined for any x and for any y, right? There is nothing to restrict the values of x and y. So x can be anything in R, y can be anything in R. So the pair x and y can be anything in R squared. So in other words, the domain of this function is the whole plane. Everything. Okay. What about z? Well, y squared minus x squared, actually it's not, it can be positive, it can be 0, it can be negative. Z might be anything. So z is also, there is no restriction on z either. So z also can be anything. Okay. Let's see if we can sketch the graph of this function inside the three-dimensional space. Z is equal to y squared minus x squared. Actually, we have seen the graph of this function. Does anyone remember what is the name of this surface? Yes, it's a saddle. It is a saddle. Yeah. Yeah, it's a saddle. So note that here the sign before x squared is negative and the sign before y squared is positive, right? So the saddle with these signs, it looks like this. It's in direction of y, it's like this. In direction of x, it's like this. And the saddle looks like this. This is how this saddle looks like. So this is the graph of this function. So here we have the graph of the function. What is the next step in order to understand this function? The next step is to look at the level curves. So for example, what are the points where, so again, let's think about it as a mountain. It's like more like a valley rather than a mountain, right? It's again, let's think about the elevation from the sea level. So for example, what are the points where z is 0 there? That's a good question. So it might be hard to see on the graph of the function, but actually there is a line here which is exactly on the surface of this function, which goes to infinity, and there's another line which is exactly on the surface of this function. It might be a little hard to see, but there are two straight lines on the surface of this function. So it means if someone exactly walks on this line, on this valley, that person would never go up or down. You can just walk on a straight line and the height would never change. Okay, let me show that to you. So let me sketch the graph of this function one more time. The graph of the function is like this. That's the graph of the function. Now I want to see what are the points where z is equal to 0. And I told you there are actually two lines. There are two lines. There are two lines which they lie on the surface of the function. Actually, yeah, that is correct. They are on the surface of the function. On the graph of the function. That's the better way to say it, is that they're on the graph of the function. How can I see that? Well, if z is 0, remember z is equal to y squared minus x squared. That is equal to 0. Well, which means y squared is equal to x squared. Now I can take the square root of both sides. Y would be plus or minus x. Remember, I wouldn't put plus or minus here too. That's it's not necessary. If you put plus or minus on one side, that would be. So what is, well, I mean, we have two lines. One of them is y equals x. That's one line. The other one is y equals minus x. These are the two lines I was talking about. So if this is the mountain or the valley or the mountain in like 3D, and this is, say, our two-dimensional map, which the domain of function is everywhere. If I look at the points, if I look again, if I'm looking at this mountain from above, what I would see is that there are two lines which they are on the surface of this mountain, and the height does not change. So these two lines are y equals x and y equals minus x. So if you want to pass this alley, this valley, the easiest thing to do if you want to see it on the map is just to walk on these lines. These lines, they're exactly where the height is 0. You are not above the sea level, you are not below the sea level either. So what are the points, for example, where the elevation from sea is 1? Say there are 1, okay? That means y squared minus x squared is equal to 1. Does anyone know what is the graph of this? What is the graph this thing represents? Okay, yeah, so actually y squared minus x squared, it looks like this. This is a curve which comes here, it then goes back up, and it has two connected components. It's a hyperbola, right? So this is called a hyperbola. And then we can look at, so this is where the height is 1. We can look where the height, for example, is 2. We would get y squared minus x squared equals 2. Well, it's similar, it's above this one. And then on the other side, it's below the green one. And we can continue doing that. For example, what if the elevation from sea is 3? It means x squared minus y squared minus x squared is 3. That would be like this. On our graph, though, on the graph of the function in the 3-dimensional case, so where the elevation, where z is 1 is actually looks like this. This is, if I want to see that on the graph of the function, it would look like this. So these two blue curves here are exactly the things we have here and here. The red lines here and here are what we have on our 2-dimensional case here and here. You see, so there is a correspondence. For example, where the elevation from sea level is 2, we would have these things, right? These are the points on the mountain where the height is 2. These blue curves, they correspond to these blue curves, and etc. Now we can look at the points on this mountain where they are below the sea level, right? So what happens? For example, z should be minus 1 rather than 1. So I change the value of z to minus 1. It means y squared minus x squared should be minus 1. Or in other words, x squared minus y squared equals to 1. Now, this is actually another hyperbola, but it's a hyperbola here. So this is where the elevation from sea level is minus 1 rather than 1. Now, where is it on the graph of the function? Well, actually, that's here. If this is where minus 1 is, on this mountain, these are, for example, the points on this saddle or on this mountain where the elevation from the sea level is mountain 1. And then there is another curve on the other side of the mountain, which is not towards us. That's this curve on the other side. My sketching skills is not very good, but it's on the other side. And then we can continue with z equal to -2 and etc. And we would get more of these hyperbolas. Z equals to -2, -3, etc. So we have a 3-dimensional understanding of this function, and we have a 2-dimensional understanding of this function, and both of them are important. Both of them are helpful, and yeah. And I see someone has suggested in the comments to look at CalcPlot 3D. That's really a good idea. When you're dealing with these functions, it's really good to sketch it with a software, so you can rotate, zoom in, and look at the graph of the function from different angles. That's a very good idea. Okay. Now let's move to another example. Is there any question here? Okay. So I know we have some students here who their major is economics. And there is a function introduced in the book, one example of a 2-variable function. So it has f of x and y, which actually, it's a 2-variable function which is usually used in economics. It's known as Cobb-Douglas production function. So there are kind of 2 variables. I mean, if you're not interested in economics, you can just think about x and y as x and y. It really, you don't need to think about them as something which represents something real in economics. But if you're interested, x is a unit of, say, labor, and y is a unit of, say, capital. And this function is defined to be a constant. C is a constant, a number, just a constant number, like 10, 100, whatever, times x to the alpha, which alpha is another number, another constant number, which is between 0 and 1. For example, alpha can be 1/2 or something like that, times y to the power 1 minus alpha. And then this, if we let that to be equal to z, then z is supposed to show us kind of number units produced by, well, when the labor is equal to x and capital equals to y. Anyway, this is just a function. So let's look at one example to see how this thing works. There is an example in the book, which I'm just telling you about that example. The example says, suppose we have a toy manufacturer, okay? And they think if the variable which measures the labor is x, and the variable which measures the capital is y, the constant c should be given to us. The constant c here is estimated to be 100, and the constant alpha is estimated to be 0.6. Suppose these are parts of the equation, the given, the parts of the question, okay? So we know the number of units produced, which we show it with z, by Cobb-Douglas production formula should be C, which is 100, x to the alpha, which is x to the power 0.6, y to the 1 minus alpha, which is 0.4. Okay, that's the number of production. Okay, now the question, a question you might, for example, ask is compare the production level when, for example, x is 1000 and y is, say, 500, with the production level when x is 2000 and y is 1000. Okay, so that's the question. Okay, so let's understand this question. So the question says when x is equal to 1000 and y is equal to 500. So first, let's understand what is the production in that case. So in that case, it means we should just compute f of 1000 and 500, which is equal to 100x to the alpha, which is 1000 to the alpha, which here is 0.6, y, which is 500 to 1 minus alpha, which here is 0.4. It's almost equal to 76. Okay. Now, what is the production when x is 2000 and y is 1000? Well, it's 100 times 2000 to the power 0.6 times 1000 to the power 0.4. And that's almost equal to 152. Okay. Now, if I look at the domain of the function, this function, well, I mean, x and y should be positive, right? It doesn't make sense to be negative. We are talking about a question in economics, that the unit of the number of units of labor and units of capital, they are positive numbers, so x and y. We can think about level curves again here. Here we have a function f, which is equal to 100, x to the 0.6, y to the power 0.4. We can think about level curves. What does a level curve mean? So, for example, we know if x is 1000 and y is 500, we would get 76. So are there any other situation with different labor and different number of units of capital, which we would get the same production at the end? I want, for example, I want the production to be 76. But for example, I want the number of units of the labor should be less than, for example, 500. Now here x, the number of the units of labor is 1000. Suppose for any reason, as a manager, you don't like that. For example, you want x to be something around 500. You want to see what the y should be, or anything like that, okay? So in these situations, a good idea is to look at the level curve. So the level curve would be these things: x to the power 0.6, y to the power 0.4 equals 0.76. You can use, actually, for these questions, these are more applied questions rather than theoretic questions. You can use calculator or Wolfram Alpha or whatever to sketch the graph of these things. Actually, it would look like a curve like this. It would look like a curve. The curve would be something like that. For example, where x is 1000 and y is 500. We are at this point. So for example, if you want the number of units of labor to be 500, you should see what is the same point, and you want this is the curve where the production is, say, 76. For all these x and y's on this curve, the production is 76. So for example, you want to see if the number of units of labor is 500, what should be the number of units of capital? So you would get 76 as the production at the end. You should see what is the y of this point. You should find this value here. And well, this is something on level curve. It's something we can compute easily. So for example, we should solve this equation. I don't solve it. You can do it simply, but you can do it with calculator, but then you would get some value here. I don't know, say 700. So this is quite important formula, the Cobb-Douglas production function, and it's quite useful to compute the production level. And it's an example of a function which has two variables. And you can, again, look at the level curves here. So it's really an example of something we are studying. Okay. Now let's go one step further. Up to this point, we mostly talked about functions from R2 to R. But we can also consider the functions from R3 to R, three-dimensional functions. Okay, so we would have three independent variables, x, y, z. And then they show the inputs. They are the input of the function. And let's show the output with w. Okay. So domain of the function, first of all, in this case, domain of the function, unlike the previous case, here the domain of the function would be something inside R3, three-dimensional space. What about the graph of the function? Well, I mean, previously, which we had two variables, the graph of the function was three-dimensional. Now that we have three variables, if we consider the output two, together there are four variables. So the graph of the function should be something four-dimensional. So we can't see the graph of the function anymore. We can't see subsets of four-dimensional space. So we can't, unfortunately, we can't really see the graph of these functions. The third thing we had, there were level curves in two-dimensional case. Actually, we don't have level curves here. Here we have level surfaces. We would see that in an example. So let's look at an example of a function from three-dimensional space to R. So let's say we have a function f, which takes three variables, x, y, and z. And say this function is equal to 4x squared plus y squared plus z squared. Okay. So the first thing to study about this function is what is the domain of the function? Well, there doesn't seem to be any restriction on x or y or z. So x can be anything in R, any real number. Y can be any real number. And z also can be any real number. So if you look at the triple x, y, and z, they can be any real number in R3 in three-dimensional space. In other words, this three-dimensional space, all of it is the domain of the function. So everything in this three-dimensional space is a point in the domain of this function. Okay. Now, so we can't see the graph of the function anymore. That is correct. We can't see the graph of the function. So there is no hope in order to see the graph of the function. There's no way to see that. And that's very sad. You see how many beautiful surfaces we had? There are more beautiful things, I'm sure, in four-dimensional space, which we can't see. That's very unfortunate. Anyway, although we can't see the graph of the function, instead of that, we can see the level surfaces rather than level curves. What does that mean? Okay, let's go to the next page. Let's have an analogy. If the real mountain we had in the previous examples is something three-dimensional and its map is something two-dimensional, now that we are dealing with objects now, which the real thing is four-dimensional, the real thing, which we can't see, the map we should have for that thing, what should be the dimension of the map? What should be the dimension of a map of a four-dimensional space? It's three-dimensional. So you see, when we are thinking about, say, mountains and things like that, there are really three-dimensional. So their map is two-dimensional. But here for us, the graph of this function, so for example, if I define W to be f of x, y, and z, which is 4x squared plus y squared plus z squared. Here we have four variables, right? 1, 2, 3, 4. So the graph of this function would be something in R4. The map we would have for this function would be something in R3. So the map should be something in R3. Okay. How can we see that? So look at the three-dimensional space. This is our three-dimensional space, right? Look at the different, just like the elevation from sea level, we used to say, so here this thing is equal to the function f. We used to say let f to be 0, let f to be 1, let f to be 2, etc., right? We were giving different values to f. We should do the same thing here too. The difference is that we had, when we used to do that, let's look at one of the examples, like for example here, when I say let's f to be 0 or let's take f to be 1 or 2 or etc., my map is two-dimensional. And for each of these things, for example, if I take f to be 0, what I would get is a curve. A curve is one-dimensional, right? If I take f to be 1, I would get another curve, another one-dimensional object. If I take f to be 2, I would get another curve, another one-dimensional object. So if my map would be two-dimensional, and these level sets, they are one-dimensional. Now here that my map is three-dimensional, these level sets are two-dimensional. So when the map is two-dimensional, the level sets are curves, and curves are one-dimensional things. But now that my map itself is three-dimensional, my level sets, actually they become two-dimensional. They are not curve anymore. And two-dimensional means they're surface. Two-dimensional objects are surfaces. Let's see that. So if f is 0, for example, we would get 4x squared plus y squared plus z squared equals 0. What is this thing? What is the surface this equation is describing? Does anyone know? No, you're close, but it's not really an ellipsoid, it's just a point. It's an ellipsoid, yeah, it's an ellipsoid, but its radius is 0. So why is that? Because 4x squared is non-negative, y squared is non-negative, z squared is non-negative. If their sum is equal to 0, each of them have to be 0. So x equals y equals z equals to 0. Okay, the first one is not really a surface, it just became a point. But actually we have seen that before in two-dimensional case too. Look at that. Here, if we take z to be, for example, 8, we don't get a curve, we just get a point. So sometimes that happens. Okay, let's go back. What if f is 1? If f is 1, 4x squared plus y squared plus z squared would be 1. That's an ellipsoid now. And that ellipsoid, in order to see how it looks like, we should divide everything by 4. Let me do that. So it would be x squared plus y squared over 4 plus z squared over 4 equals to 1 over 4. This ellipsoid is more extended in y and z direction rather than x. So, well, it's a little challenging to sketch it really for me too. So this is what we would get instead of a curve. So in the previous picture, we had these curves. Exactly the object which plays the role of that curve here is this surface. So for example, if f is 2, then it means 4x squared plus y squared plus z squared equals to 2. After dividing by 4, the equation I would get is equals to 2 over 4. And then, well, I want it to be equal to 1. I have divided by, I should divide it by 8. So it would be over 8. Over 8 over 8 equals 1. So these are a little bit more extended. This ellipsoid is a little bit bigger. It's a little more extended in each direction. So, and then we can continue that for, say, f of equal to 3, f equal to 4, and we can try that, and we would see we get larger and larger ellipsoids, which each of them contains, in some sense, has the previous one inside it. Inside the area, it's closed. So rather than having curves, here we have surfaces. That's the higher dimensional example of this thing. Okay. So if you look at the section, if you look at the chapter 13, 13.1, there is a section called computer graphics. There are some beautiful pictures to take a look at. There are some level curves. You can look, they're interesting. I would recommend you to look at that later. And that was the ending of the section 13.1. We finished the section 13.1. Is there any question? So there's a question. Let me understand the question. What part is two-dimensional? Well, these surfaces, this is an ellipsoid, right? An ellipsoid is two-dimensional thing. It's a surface, like a sphere, like a balloon. It's a two-dimensional thing. So we used to have curves, right? We used to have level curves. For example, here we have these curves. These curves are one-dimensional. They're like a line. They're one-dimensional, if I understand your question correctly. Here, rather than having level curves, we have a level surfaces. And each surface itself is a two-dimensional object. Does that make sense to you? Also, is there any other question? Okay, that's good. Well, W is not, okay, the question is what domain is W in? There are two things to note. One is that since W is equal to 4x squared plus y squared plus z squared, these are all non-negative. Their sum would be non-negative, so W would be greater or equal than 0. But we usually don't call that domain because we usually say domain when we are referring to independent variables, like the domain of a function from R to R. For example, here we write y equals f of x. We say domain for this one. For y, we usually call it codomain. So, and then the codomain here is W greater or equal than 0. Yes. Okay, so if there is no other question, let's have a very short break. Let's continue at 10 with section 13.2.